All right, in this one, we have a gumball that's rolling down a ramp as seen in this picture here, and we want to determine the equation for acceleration of the gumball down the ramp in terms of the angle of the ramp. So if we consider this gumball that's rolling down the ramp, we can go ahead and draw that portion of it there. And we can draw our forces on that. So we know we have the normal force, force of gravity, and friction going back. We have the force of gravity in the x, force of gravity in the y. And we can talk about the linear motion in terms of this, right? We know that the force of friction plus the positive force of gravity in the x equals ma. So we're familiar with that, and we've done that in the past. Now, in terms of angular motion, we know we have friction, right? We have the normal force, we have the force of gravity. And the force of friction is the only force causing torque. So that's what's causing the rotation, the force of friction. So if we consider the sum of the torques equals the moment of inertia times alpha, we're dealing with, a sphere here, so 2/5 mr squared is a sphere, and we have torque due to friction. We can put the force of friction times r, which is the radius from the center of the gumball to the edge, so that's r, and then we have friction times the force of friction causing the torque, so we have that, and then we want to figure out what the acceleration is. So no, the linear acceleration is equal to r times alpha, and therefore if we rearrange this, we can get this is the alpha equals the linear acceleration over r. And so what we can do is we're coming back through and taking this, and so what we can do is we can place in for alpha here, we can place the linear acceleration divided by the radius, and therefore we can get this in here in terms of the linear acceleration. So this is linear acceleration, this is the radius, and what we can do is the radius will cancel out, this radius here will cancel out, and we can, divide both sides by radius, then we can cancel these out here. So we're left with the force of friction is 2/5 ma, and that's linear acceleration. And so when we place this into here, we have 2/5 ma, and again, this is the linear acceleration, so we have it in terms of linear now, and we can divide both sides by mass, and we get the variables in terms of linear acceleration. We can solve for add both a to both sides, so we get 7/5 a equals g sine theta. And this is the linear acceleration. The linear acceleration is 5/7 g sine theta. And so that's going to be the acceleration of the gumball down the ramp. So let's say the gumball is at a height of 3 centimeters and is moving 0.25 meters per second initially. We want to figure out how fast it is at the bottom. And so we want to find out using conservation of energy first, and then we can find using the acceleration of the ramp. And so we can see how this works both ways. So if we outline what we have, if there's no frictional loss in terms of sliding friction in terms of air resistance, there's no non-conservative work, we'll assume. So the change in kinetic energy translational plus the kinetic energy rotational change plus the change in potential energy will all add up to be 0. There's no springs involved, so we don't have that in here. And so we've got that. So if we unpack all those, we have the kinetic energy final minus kinetic energy initial translational that we're so used to. And then in terms of rotational, we have the 1/2 I omega squared final minus 1/2 I omega squared initial, which is the rotational part that we're introducing in this unit, and then the gravitational, how much does that change? So when we think about the rotational versus the linear, again, if we take r times omega, the radius times the angular speed. That will give us the linear velocity. And so what we're going to do is we're going to place those so rearranging V over R, we're going to place that into the equation. We have our sphere, which is 2/5 mr squared. That's the moment of inertia. So we can place our values in there, V over R, and then this is squared. So in here, both the top and bottom are squared. Both the top and bottom are squared because, it's omega squared. So V squared over R squared. And then we can place our sphere in there. So we know the moment of inertia for the sphere. And you can already see how our, some of the variables are going to cancel out. R is going to cancel, R squared is going to cancel from both. So we've got that. We can divide both sides by mass as well. And so the mass is gone, so we end up with this here. And if we continue to simplify, and we have these values, we know that the initial velocity is 0.25. We know the initial height is 0.03 meters. And we can figure out what the velocity is at the bottom. So we'll continue to simplify there. We'll end up getting 0.7 meters per second is how fast it'll be going at the bottom using conservation of energy. And so if we consider now the gumball in terms of what we did with acceleration, we have the equation that we got before, 5/7 g sine theta, and we know the initial velocity. We're looking for the final velocity, and in this case here, we need to know how far it goes. And so if we set up our trig here, we know the angle is 21 degrees, so we can figure out the hypotenuse, and the hypotenuse is 0.084. So that's how long this portion is right here as the gumball is going to go down. So if we know that, and we know that we can get the acceleration, we can figure out what V final should be using our constant acceleration equation. So go ahead and pause the clip. Why don't you go ahead and try this one, and then when you're ready to check it, you can hit play to continue. Okay, so you should have used V final squared equals V initial squared plus 2a delta x, because we have the linear acceleration. The linear acceleration is 2.51 meters per second squared, and we should get the same final velocity, 0.7 meters per second. All right, so now we want to derive the equation for this system as we continue to practice how this works. So this is a mass cylinder that's at the top of the ramp, and it's going to be rotating down as it spins down, and so therefore there is friction. And we want to determine the acceleration of the system. So just like the last one, we have to deal with the sum of the torques equals I alpha, and then also what's going on with the incline in terms of the sum of the forces. And so, yeah, go ahead and pause the clip and give your best shot with that. You're going to have to eventually bring this into here to find what the linear acceleration is and for this system. So yeah, go ahead and pause the clip and do your best with that. And when you're ready to check, you can hit play to continue. All right, so we've got friction acting backwards to make it spin, and so we have it ready to get it to spin. Positive force of friction times the radius equals 1/2 mr squared alpha. 1/2 mr squared is the moment of inertia for the cylinder, and we can rearrange to get our alpha into what's linear, so which is linear acceleration divided by the radius, which will look like this. And then our two radii will cancel out there. We divide radius from both sides. We should get 1/2 ma. And we can come over to our ramp. We look at our forces. We have our normal force, force of friction, force of gravity. And therefore, this side of the triangle is mg sine theta. It's the opposite side. The hypotenuse is mg. And again, if the intuitions, you're still struggling a little bit with your trig, so there's no problem just, working through that, right? This is the angle, this is the angle, and using showing the whole trig there. All right, and so negative force of friction plus positive force of gravity x equals ma, and we can bring this over and plug it in. Mass cancels from both sides, and we're left with negative 1/2 a plus g sine theta equals a. We can add this to the other side and then divide. So this is the acceleration of the system. This is again for a cylinder that's rolling down an incline and is not slipping. It's just, the friction there is helping it roll. And yeah, and that's what we got. So if we want to compare this to where we had before, remember we used energy and we solved for the final velocity at the bottom there, 6.26 meters per second. And so yeah, let's see if we get the same thing here. So the height of the ramp is 3 meters. The angle of the ramp is 40 degrees. Therefore, the hypotenuse of the ramp is 4.667 meters. And so we got the height here. We've got the length of the ramp. And so that is going to be S. V initial is 0 up here. V final is what we're looking for down here. And we can find the linear acceleration right here. So yeah, go ahead and pause the clip and see if you get the same thing as the energy there. And then when you're ready to check, you can hit